Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today, we're diving into atomic structure and the periodic table. Understanding atomic structure is essential for making sense of periodic trends like effective nuclear charge, atomic and ionic radius, ionization energy, and electronegativity, all of which we will cover in this video. But before we explore these trends, we first need to understand subatomic particles and how they determine an atom's properties. Let's go ahead and get started. Every atom is composed of three fundamental subatomic particles. Protons are positively charged particles that are found in the nucleus. Neutrons are neutral particles, meaning they carry no charge, and they also reside in the nucleus. And electrons are negatively charged particles that orbit around the nucleus in electron clouds. Each of these particles plays a crucial role in defining an atom's identity and behavior. To better understand their properties, let's look at the following table. What we notice is that protons and neutrons have identical masses, both approximately 1 atomic mass unit, or about 1.67 times 10 to the negative 27 kilograms in standard units. Electrons, on the other hand, are significantly smaller, about 0.0005 atomic mass units, which is nearly 2,000 times lighter than a proton or neutron. In terms of charge, protons again carry a +1 relative charge, electrons carry a -1 relative charge, and neutrons are uncharged. Now that we've established the properties of subatomic particles, let's go ahead and focus on the proton, because the proton plays the most significant role in determining an atom's identity. The number of protons in an atom is called the atomic number. The atomic number is unique. It defines each element. For example, oxygen has an atomic number of 8, meaning every oxygen atom contains exactly 8 protons. If an atom had 9 protons, it would no longer be oxygen. It would be fluorine. Because all atoms of an element contain the same number of protons, the atomic number serves as the fundamental identifier for every element on the periodic table. While protons define an element, protons and neutrons collectively contribute to the mass. The mass number of an atom represents the total number of protons and neutrons in the nucleus. Neutrons, they do not affect the atomic identity, but they do determine an atom's isotope. These are atoms of the same element that have different numbers of neutrons. For example, for oxygen, the atomic number 8 tells us there are 8 protons in every oxygen atom. The mass number is approximately 16, meaning most oxygen atoms have 8 protons and 8 neutrons, since 16 minus 8 is equal to 8. In addition to this, in a neutral atom, the number of protons is equal to the number of electrons, and that balances out the charges. However, atoms can gain or lose electrons and form ions. Cations are formed when an atom loses electrons, and that results in a positive charge. Anions are formed when an atom gains electrons, and that results in a negative charge. The magnitude of the charge directly corresponds to the number of electrons that are lost or gained. So to summarize, The atomic number is the number of protons, and it defines the element's identity. The mass number is equal to the number of protons and neutrons. And in a neutral atom, the number of protons is equal to the number of electrons. Now that we understand atomic structure, let's take a closer look at the periodic table and how elements are categorized based on their properties. The periodic table is organized into groups. Groups run vertically and they're numbered from 1 to 18. The periodic table is also organized into periods. These run horizontally and they're numbered 1 through 7. Certain groups on the periodic table have specific names because their elements share unique chemical behaviors. So group 1 over here is known as the alkali metals. They include elements like lithium, sodium, potassium, and so on. These metals are highly reactive, especially with water, and they easily lose one electron to form +1 cations. Group 2 right here, they're known as the alkaline earth metals, and they include elements like beryllium, magnesium, and calcium, so on. These are less reactive than alkali metals, but they still readily form +2 cations. Then over here is group 16. This is known as the chalcogens group. This group includes oxygen, sulfur, selenium, and so on. These elements, they tend to gain 2 electrons to form 2 minus anions. Group 17 is known as the halogens. It includes elements like fluorine, chlorine, bromine. And these are also highly reactive nonmetals. They tend to gain 1 electron to form -1 anions. Finally, group 18 is known as the noble gases, and this group includes helium, neon, argon. These are inert, non-reactive gases due to their full valence shell, meaning they rarely form bonds. Now let's classify elements based on their properties. We have 3 main classifications: metals, nonmetals, and metalloids. Let's start with discussing metals. Most elements on the periodic table are actually metals, and they're found on the left side and in the center of the table. Metals have distinct properties. First, they are good conductors of heat and electricity. They are malleable, meaning they can be hammered into thin sheets. They're also ductile. That means they can be stretched into wires. They also have a shiny appearance, and they tend to lose electrons and form positively charged cations. Nonmetals, on the other hand, are found mostly on the right side of the periodic table, and they have opposite properties to metals. All of the nonmetals here are boxed in this dark blue color. Nonmetals are poor conductors of heat and electricity. In fact, they act as insulators. They are not malleable or ductile. Instead, they are brittle in solid form. They also lack luster and they typically appear dull, and they tend to gain electrons and form negatively charged anions. Then between metals and nonmetals, there's a small category of elements called metalloids. All of the metalloids that you see on the periodic table have a blue dot associated with them. So these are the metalloids. These elements are going to share characteristics of both metals and nonmetals. Some metalloids are semiconductors, meaning they conduct electricity under certain conditions, which makes them essential in materials like computer chips and solar panels. Their chemical behavior can also vary depending on the element they are bonding with. Sometimes they act like metals, other times like nonmetals, again, depending on the element they are bonding with. And, and one more thing is that all of the elements you see here with a blue dot, those are metalloids. Why does this classification matter? Well, understanding these categories helps us predict chemical behavior, and it helps us answer questions like, why do metals form cations while nonmetals form anions? Why do metalloids play such a unique role in material science and technology? And how can we use the periodic table to determine the properties of an element? With this framework in mind, we're now ready to explore how periodic trends affect atomic properties. We're going to start with understanding shielding and effective nuclear charge. These concepts actually influence atomic size and ionization energy, which we're going to cover today as well. Let's start with shielding. Shielding, sometimes called the shielding effect, refers to the ability of inner core electrons to reduce the attraction between the nucleus and the outermost valence electrons. Electrons in lower energy levels that are closer to the nucleus create a shielding barrier that weakens the electrostatic pull felt by the outer electrons. The more core electrons an atom has, the stronger the shielding effect. This means that valence electrons in larger atoms experience less attraction to the nucleus. Electrons in the n=1 shell, they don't experience any shielding at all. Since they're the closest to the nucleus, they feel the full strength of the nuclear charge. To help us understand this, think of shielding like being at a concert. If you're in the front row, there's nothing blocking your view. You get to experience the full energy of the performance. You get to really observe the performer, just like an electron in the n=1 shell. It gets to feel the full nuclear charge experience. However, as you move further back, you get seats that are further away from the stage. More people stand between you and the stage. The farther you are, the more difficult it becomes to see clearly and experience fully because the crowd is blocking your view. Similarly, core electrons act as a barrier, reducing the pull of the nucleus on those outer valence electrons. The more core electrons there are, the stronger the shielding effect and the weaker the attraction between the nucleus and the outermost electrons. Now, how does shielding change across the periodic table? So this is different than the trend for effective nuclear charge, but we're going to take a look at this page and work through it. Down a group, as you go down a group, shielding increases because additional electron shells are added, meaning more core electrons are present to block the nuclear charge. In other words, additional electron shells are added as you move down a group, meaning more core electrons are present to shield the valence electrons. What about across a period? What is the trend for shielding? Across a period, shielding actually remains relatively constant. Why? Because no new inner shells are added. Only valence electrons increase. That's because every row is associated with a principal quantum number. So we're adding electrons as we move across a period to the same shell. Now, these new electrons that are being added to the same energy level are not going to be affecting the core electrons, so no additional shielding occurs. Now that we understand shielding, let's talk about effective nuclear charge. These two ideas are interrelated, but they're distinct, so pay attention. Effective nuclear charge is the net positive charge that valence electrons actually experience after accounting for shielding. It considers both the attractive force from the protons and the shielding effect from the core electrons. And the effective nuclear charge is calculated using this equation right here. The effective nuclear charge is equal to Z minus S. Z is the atomic number. This is the total number of protons for an atom. And S is the number of shielding electrons, aka the number of core electrons, the number of electrons between the valence electrons and the nucleus. The reason we subtract S is that the core electrons reduce the full attractive force of the protons on the valence electrons. So, looking at the periodic table, what is the trend for effective nuclear charge? Across a period, the effective nuclear charge increases. Although more electrons are added, they're going into the same energy level. So shielding remains relatively constant, like we said before, but there's an increasing number of protons as you move across a period. And this increasing number of protons pulls the valence electrons in closer, and that strengthens nuclear attraction. It also makes the atom smaller and it increases the ionization energy, but we're going to cover that shortly. So the trend is that across a period, the effective nuclear charge increases. What about going down a group? What is the trend for effective nuclear charge? Down a group, effective nuclear charge decreases. Even though the number of protons increases as you go down a group, so does the number of inner electron shells, and that's going to increase shielding. This increase in shielding is going to weaken the attraction between the nucleus and the valence electrons, which is why effective nuclear charge decreases as you move down a group. Now let's apply this concept to two elements. For example, fluorine. Fluorine has an atomic number of 9. That means it has 9 protons and 9 electrons in a neutral fluorine. The first step we want to do here to understand the effective nuclear charge of fluorine is we want to write down its electron configuration. The electron configuration for fluorine is 1s2, 2s2, 2p5. From here, we need to determine the number of valence electrons. There is a total of 7 valence electrons. That means the other 2 electrons are the core electrons. Now that we know that, the number of core electrons and the atomic number for fluorine, we can go ahead and calculate the effective nuclear charge. It's going to be equal to Z minus S. Z is the atomic number. S is the number of core electrons. So this is going to be 9 minus 2. That's equal to positive 7. This means that the valence electrons in fluorine feel an effective nuclear charge of plus 7. Now let's apply this concept to another example. Let's do sodium. Sodium has an atomic number of 11. So that means it has 11 protons. The first thing we want to do is we want to write the electron configuration for sodium. It is 1s2, 2s2, 2p6, 3s1. Sodium has 1 valence electron and 10 core electrons. With this information, we can go ahead and plug in our values for the atomic number of sodium and the number of core electrons and calculate the effective nuclear charge. The effective nuclear charge is equal to 11, the atomic number, minus 10, the number of core electrons. This gives us a value of positive 1. This means that the valence electron in sodium experiences an effective nuclear charge of +1. So in summary, the shielding effect occurs when inner electrons block the attraction of the nucleus for outer electrons. The effective nuclear charge is going to be the actual nuclear charge an electron experiences. Across a period, effective nuclear charge increases. Down a group, effective nuclear charge decreases. Now, among the subshells, the shielding effect is going to follow the following order. 4F has a greater shielding effect than 3D, which has a greater shielding effect than 2P, which has a greater shielding effect than 1S. Meaning, 4F electrons experience the most shielding, and 1S electrons experience the least shielding. Now, let's tackle some practice problems. While we tackle these problems, I want you to keep in mind that effective nuclear charge represents the net positive charge felt by an electron after we account for the shielding effect of those inner core electrons. Since effective nuclear charge is equal to the atomic number minus the number of shielding electrons, a higher effective nuclear charge indicates less shielding and a stronger pull from the nucleus. This first problem asks us, how many core electrons are in the second shell of neon? To solve this, recall that core electrons are those in inner shells that shield valence electrons from the nuclear charge. Neon has an atomic number of 10, meaning it has 10 protons and 10 electrons. Its electron configuration is 1s2, 2s2, 2p6. From the electron configuration and our rules for valence electrons, which we covered in our special topics electron configuration video, neon has 8 valence electrons. It has 8 valence electrons. That means it has 10 minus 8 core electrons. That is equal to 2 core electrons. In other words, that first shell, 1s2, it contains 2 electrons, and those act as core electrons for the second shell, the 2s2, 2p6. The correct answer here is A. The next problem says electrons in which shell would experience the least shielding effect. Shielding occurs, again, when inner core electrons block the attraction between the nucleus and the outer valence electrons. The closer an electron is to the nucleus, the less shielding it experiences. The 1s orbital, that's going to be the closest to the nucleus, and that means those electrons are going to feel the full nuclear charge with no shielding from other electrons. Electrons in orbitals like 2p, 3d, 4p, they experience more shielding due to the presence of inner electrons. Therefore, the correct answer here is going to be A, 1s. The last and final problem for effective nuclear charge and shielding says, which of the following electrons experiences the strongest effective nuclear charge? Again, effective nuclear charge is the net positive charge felt by an electron, and it's calculated as the difference between atomic number and the number of core inner electrons. Electrons in lower energy levels, meaning closer to the nucleus, are going to experience a stronger effective nuclear charge because they're less shielded. So let's work through the given choices. A says an electron in the 2s orbital of lithium. Lithium has an atomic number of 3, meaning it has 3 protons, and since it is neutral, it also means it has 3 electrons. Let's go ahead and write the electron configuration for lithium. It's 1s2, 2s1. This tells us that lithium has one valence electron and two core electrons, so S is going to be equal to 2. We have both pieces of information we need to calculate the effective nuclear charge for lithium. It's going to be equal to 3 minus 2, which gives us positive 1. Let's go ahead and move on to B. B says an electron in the 3p orbital of sulfur. Sulfur has an atomic number of 16, which means it has 16 protons and 16 electrons since it's neutral. Let's go ahead and write the electron configuration for sulfur. It's going to be neon, 3s2, 3p4. It has 6 valence electrons. If it has 6 valence electrons and we know it has a total of 16 electrons, that means that the other 10 electrons are going to be our core electrons. And that gives us our S value. Our S value is equal to 10 and our Z value is equal to 16. So we can go ahead and calculate the effective nuclear charge for sulfur. It's going to be equal to 16 minus 10. That gives us plus 6. C says an electron in the 4d orbital of zirconium. Zirconium has an atomic number of 40. Has an atomic number of 40. Let's go ahead and write its electron configuration. It also has 40 electrons since it's neutral. The electron configuration for zirconium is krypton, 5s2, 4d2. 5s2, 4d2. It has a total of 4 valence electrons. If the total number of electrons for zirconium is 40, and we know that 4 of them are valence electrons, that means the other 36 are the core electrons. That means our S value is equal to 36. Now we can go ahead and calculate the effective nuclear charge for zirconium. It's going to be 40 minus 36, and that's equal to plus 4. Now for our last and final option, we have an electron in the 5p orbital of iodine. Iodine has an atomic number of 53, meaning it has 53 protons, and it also has 53 electrons since it's neutral. So our Z value for iodine is 53. Let's go ahead and write the electron configuration for iodine. It's going to be Kr, 5s2, 4d10, 5p5. The number of valence electrons it has is going to be 7. If it has 7 valence electrons, and we know the total number of electrons is 53, then 53 minus 7 is 46. 46 is the number of core electrons that iodine has. So this is going to be our S value. We have both pieces of information to go ahead and calculate the effective nuclear charge for iodine. It's going to be equal to 53 minus 46, and that gives us plus 7. Since the 5p electrons in iodine has the highest effective nuclear charge of plus 7, it's greater than any of the other values we calculate, it's going to experience the strongest effective nuclear charge among the given choices. So the correct answer here is going to be D. Next, we want to go ahead and discuss atomic and ionic radius. Atomic radius is defined as the distance from the nucleus to the outermost electron in an atom. Since atoms don't have a definite boundary, we typically estimate atomic radius based on the distance between two bonded atoms, and we divide that value in half. So that's where we get our values for atomic radius. let's examine how atomic radius changes as we move across the periodic table. Across a period left to right, atomic radius decreases, and down a group, atomic radius increases. Let's discuss why that is the trend. So, across a period, left to right, atomic radius decreases. Well, as you move from left to right across a period, protons are added to the nucleus, and that's going to increase the nuclear charge. This stronger attraction actually pulls the valence electrons closer to the nucleus, leading to a smaller atomic radius. Even though electrons are also added, yes, they go into the same energy level, meaning shielding remains relatively constant. For example, lithium has a larger atomic radius than fluorine because lithium's nucleus exerts a weaker pull on its valence electron compared to fluorine's. The other trend is that down a group, top to bottom, atomic radius increases. Why? Well, when you move down a group, each successive element has an additional electron shell, which increases the size of the electron. Although the nuclear charge increases moving down a group, shielding also increases due to the presence of more inner electrons, and that counteracts the pull of the nucleus on the outermost electrons. Hence why atomic radius increases moving down a group. This means that potassium is much larger than lithium because potassium has more electron shells. Now, what about ionic radius? Ionic radius refers to the size of an ion, which depends on whether an atom has lost or gained electrons. Let's cover both cases. Cations, which are positively charged ions, they're going to be smaller than their neutral atoms. This is because when an atom loses electrons, the remaining electrons experience a stronger nuclear pull, causing the ion to shrink. Additionally, removing electrons may also mean losing an entire electron shell, making the ion even smaller. For example, sodium, Na, neutral sodium, it has a larger radius than sodium plus 1 because sodium plus 1 has lost its outermost electron. What about anions? Anions, these are negatively charged ions, they're going to be larger than their neutral atoms. When an atom gains electrons, electron-electron repulsions increase, and that causes the electron cloud to expand. So as an example, fluorine has a smaller radius than fluorine minus 1, which has gained an electron, because adding an electron increases repulsion in the outer shell. Now that we've introduced ionic radius, it's also important to understand how different ions compare in size, especially when they have the same number of electrons, but different nuclear charges. This brings us to the concept of isoelectronic species. These are atoms and ions that contain the same number of electrons, but they differ in the number of protons in the nucleus. Isoelectronic species, they follow a predictable trend in size based on effective nuclear charge. Since all species in an isoelectronic series have the same number of electrons, the key factor influencing their size is going to be the number of protons in the nucleus, and that determines how strongly the nucleus pulls on the electron cloud. The key points to keep in mind here are the following. As nuclear charge increases, the ion becomes smaller. As nuclear charge decreases, the ion becomes larger. And this happens because a higher nuclear charge pulls electrons in more tightly, and that reduces the radius. On the other hand, a lower nuclear charge results in weaker attraction, and that allows the electron cloud to expand. Let's analyze this trend for ions that each have 2 electrons but different number of protons. It's going to be this first table right here. We notice we have H minus, helium, lithium plus, beryllium 2 plus. All of them have 2 electrons, but they have different number of protons. Hydrogen has 1 proton, helium 2, lithium 3, beryllium 4. So this H minus, this hydride ion, it's going to be the largest in this set because it has the fewest number of protons, just 1, attracting the 2 electrons, meaning the electron cloud here is going to be more spread out. Then we have our neutral helium. This has 2 protons pulling in the 2 electrons. It's going to make it slightly smaller than the hydride ion. Then there's the lithium plus ion. This has 3 protons and only 2 electrons. That's going to lead to a stronger pull that makes it even smaller. And then finally, beryllium 2 plus, this has the smallest ionic radius because its 4 protons are going to exert the strongest attractive force on it, on those 2 electrons, and it's going to pull them in more tightly. So beryllium 2 plus ion is going to have the smallest ionic radius. So you notice this inverse relationship between effective nuclear charge and ionic radius. Similarly, let's analyze another set of ions. All these ions are going to have 10 electrons. We have O2 minus, our oxide ion. It has 10 electrons and 8 protons. Then we have our fluoride ion. It has 10 electrons, 9 protons. Neon has 10 electrons, 10 protons. Sodium plus has 10 electrons, 11 protons. And magnesium 2 plus has 10 electrons, 12 protons. We're going to notice a very similar trend here. All right, going from our oxide ion to our magnesium ion, the effective nuclear charge increases. And our ionic radius, going from our oxide ion to our magnesium ion, it's going to decrease. That means that our oxide ion has the largest ionic radius and our magnesium ion has the smallest ionic radius. Let's still work through each of these and talk about it. So for our oxide ion, it has 10 electrons and 8 protons. It's going to be the largest because there's only 8 protons to attract its 10 electrons, meaning the nuclear pull is weak, relatively speaking here, and the electron cloud expands. Then we have our fluoride ion. It has 1 extra proton compared to the oxide ion, so it pulls its electrons in slightly more, making it smaller. Then there's our neutral neon, 10 protons for 10 electrons, meaning its electrons experience a stronger pull than those in the fluoride ion. Next, we have our sodium ion, 11 protons for the 10 electrons, meaning there's an increase in the effective nuclear charge. And the increased nuclear charge pulls the electron cloud in, making it even smaller. Then finally, we have our magnesium ion. It is the smallest because it has 12 protons, attracting only 10 electrons. It has the strongest nuclear attraction and the tightest electron cloud. So in summary, atomic radius decreases across a period and it increases down a group. Cations are always smaller, and anions are always larger than their neutral atoms. And finally, for isoelectronic species, the ion with the highest nuclear charge is going to have the smallest ionic radius. With that in mind, let's jump into a couple of practice problems. This first problem says, which of the following elements has the largest atomic radius? Beryllium, magnesium, sodium, or potassium? To determine atomic radius, remember the periodic trend. Atomic radius increases down a group and it decreases across a period. This happens because moving down a group, atoms add additional electron shells, increasing size, while moving across a period increases nuclear charge, which pulls electrons closer. Now, the given choices are beryllium, which is right here, magnesium, which is right here, sodium, which is right here, and potassium, which is right here. Among these, potassium is the lowest in group 1, meaning it has the most electron shells and the largest atomic radius. So the correct answer here is going to be D. The next problem says, which group contains the elements with the smallest atomic radius in their respective periods? We have alkali metals, noble gases, halogens, and alkaline earth metals. Across a period, atomic radius decreases from left to right because the increasing nuclear charge pulls electrons closer without additional shielding. The noble gases are in group 18. They are at the end of each period, meaning they have the smallest atomic radii compared to other elements in their rows. Even though they have full valence shells, their strong nuclear attraction keeps the electrons tightly bound. So the correct answer here is going to be B, noble gases. The third question says, why does atomic radius increase as you move down a group? A says increased shielding and additional electron shells. B says increasing nuclear charge pulls electrons closer. C says decreasing number of protons reduces attraction. And D says more valence electrons repel each other, expanding the atom. Now, as we move down a group, there's additional electron shells that are added. This is going to increase the distance between the nucleus and the outermost electrons. The inner electrons, they're going to create shielding, and that's going to reduce the pull of the nucleus on the valence electrons. Even though the number of protons does increase as you move down a group, shielding is going to dominate, and that's going to lead to a larger atomic size. So here the correct answer for why atomic radius increases as you move down a group is going to be because of increased shielding and additional electron shells. Now we move into problem 4. This says rank the following ions in order of decreasing size. Here we're comparing sodium plus to magnesium 2 plus to aluminum 3 plus. Each of these ions have 10 electrons. So we're dealing with an isoelectronic species. These are ions with the same number of electrons, but different number of protons. And when we're comparing isoelectronic species, nuclear charge is going to determine size. Higher nuclear charge pulls electrons closer, and that reduces their ionic size. Again, all 3 ions have 10 electrons, but different number of protons. Sodium has 11 protons, magnesium has 12 protons, and aluminum has 13 protons. Since sodium has the fewest protons, it has the weakest pull on electrons, and it's going to be the largest. This is followed by magnesium, which has a slightly stronger pull on electrons and is therefore smaller than sodium plus. And finally, aluminum 3 plus, it has the most protons, meaning it pulls electrons in more tightly, and it's going to be the smallest. So the correct ranking from largest to smallest is sodium +1, followed by magnesium 2+, followed by aluminum 3+. That means the correct answer here is A. In the final problem, we're asked, in the following series, which ion has the largest radius? So we're comparing these 4 ions. Anions are always larger than their neutral atoms because adding electrons increases electron-electron repulsion, and that expands the electron cloud. When we're comparing ions within the same group, atomic radius increases as you move down the periodic table due to the addition of electron shells. More energy levels means a larger atomic radius. So let's go ahead and look at our periodic table. We have sulfur 2-, so this is sulfide, and then we have selenium 2-, this is selenide. They're both in group 16. The other 2 options are chlorine -1 or chloride and bromine -1, which is bromide. They are in group 17. Looking at just group 16, selenide Se2-, that's going to be below sulfide Se-1 in the periodic table. It has more electron shells, so it experiences greater shielding, and that makes selenide Se2- larger than sulfide, which is sulfur 2-. Okay, we figured that out. Let's look at group 17. Bromide is below chloride, so bromide is larger than chloride. Now we have to compare the 2 largest that we just determined from each group. We have to compare Se2- to Br-1. Selenide here, Se2- is going to be larger because it belongs to group 16 and it's gained 2 electrons. That's going to increase repulsion more than bromide, which has only gained 1 electron. So the correct answer here, which has the largest radius, it's going to be C, Se2-, selenide. With that, we can move into our next discussion on ionization energy. Ionization energy is the amount of energy that's needed to remove the outermost electron from a neutral atom in the gas phase. The stronger the attraction between the nucleus and the valence electron, the more energy that's required to remove it. Now, what are the general trends for ionization energy? Across the periodic table, ionization energy increases, and down a group, ionization energy decreases. Now, let's look at the periodic table and discuss why these trends are the way they are. For across a period, left to right, ionization energy increases, and this happens because effective nuclear charge increases as protons are added to the nucleus, while electrons are added to the same energy level. Stronger attraction means harder to remove an electron. What about down a group? Down a group, top to bottom, ionization energy decreases. Moving down a group, atoms gain more electron shells, which increase shielding and push valence electrons farther from the nucleus. That makes it easier to remove those electrons. These trends explain why elements on the left side of the periodic table, like alkali metals, have low ionization energy, while elements on the right, like noble gases, have high energy ionization energy. While the general trend holds, there are some exceptions, one in particular that we have to discuss. Normally, we would expect ionization energy to increase steadily as we move across a period. However, we see a slight dip in ionization energy when we're comparing elements with p4 electron configuration. comparing that to elements with a p3 configuration. Let me repeat that. We see a slight dip in ionization energy when we're comparing elements with a p4 configuration to those with a p3 configuration. To understand why, let's think about what happens when an atom has a p4 electron configuration. In this case, there is one of the electrons in the p orbitals that's going to be paired up with another electron. These electrons, though they're negatively charged, this pairing right here creates additional electron-electron repulsion, and it makes the atom a little less stable. If we remove one electron from this p4 configuration, then what happens is we achieve a half-filled p3 configuration, which is more stable because each electron gets its own orbital, and that minimizes repulsion. This increased stability means that elements with a p3 configuration will actually have higher ionization energy than elements with p4 configuration, even if the p4 element has more protons. So let's look at an example. A great example is comparing oxygen and nitrogen. Oxygen has a higher nuclear charge than nitrogen, but oxygen's p4 configuration makes it easier to remove an electron than nitrogen's stable p3 configuration. As a result, oxygen actually has a lower ionization energy than nitrogen, and that a little bit breaks the trend, but that's okay. This gives us the following ranking. That means that the ionization energy for nitrogen is in fact greater than oxygen. We see the same trend comparing sulfur and phosphorus, right? Sulfur has that p4 configuration. Phosphorus has that p3 configuration. Sulfur with its p4 configuration is going to have a lower ionization energy than phosphorus, which has a stable, half-filled p3 configuration. So we write that the ionization energy for phosphorus is in fact greater than it is for sulfur, even though sulfur comes after phosphorus. Now, more generally, this means that when an element has a half-filled or fully filled subshell, whether it's P or D, its ionization energy will be higher than expected. This is because these configurations are particularly stable, and it makes it harder to remove an electron. So far, this is all talk about the first ionization energy. That's the energy required to remove the first electron from a neutral atom. But what happens when we remove multiple electrons? Do we see a steady increase, or does something else entirely happen? So the key idea here is that subsequent ionization energies increase significantly after the first electron is removed. Once the first electron is gone, the remaining electrons experience a greater effective nuclear charge because now there are fewer electrons available to shield the nucleus. And as a result, removing any of those additional electrons is going to require much more energy. But how much more energy? Well, that depends on the configuration after each electron has been removed. Let's look at the alkali metals like sodium or potassium. All right, and then afterwards, we're also going to look at an example of the alkaline metals. All right, that's group 2. So we'll look at group 1 and group 2. For the alkali metals, group 1, the second ionization energy is dramatically larger than the first. Why? This happens because removing that first electron, removing one electron from sodium, gives it an electron configuration similar to a noble gas, which is very stable. So once an alkali metal has lost its one valence electron, the next electron must be removed from a very stable noble gas-like configuration that's much closer to the nucleus. That's going to require a significantly higher ionization energy. So removing that first electron from alkali metals requires a little bit of energy. Trying to remove that second electron from alkali metals requires a significantly higher ionization energy. That's because these inner electrons are tightly held by the nucleus. So ionization energy 2 is much higher than ionization energy 1 for the alkali metals. What about for the alkaline earth metals? So group 2, elements like beryllium, magnesium, calcium. Well, we see an even larger jump in that third ionization energy. So there is a significant ionization energy to remove the first electron and then a bit for the second, but then the highest ionization energy is going to be trying to remove that third electron, because after losing 2 valence electrons, it now has a noble gas-like configuration, and that's very stable. So trying to remove an electron from a very stable configuration requires a lot of energy. I'll give you some examples here with actual numbers. We'll do sodium. I have some numbers for sodium. The first ionization energy for sodium is about 497 kilojoules per mole. That's relatively low because removing 1 valence electron allows sodium to form sodium plus, which has a noble gas configuration. What about that second ionization energy? That second ionization energy for sodium is 4,562 kilojoules per mole. This is almost 10 times larger than that first ionization energy. And this happens because once sodium has lost its first electron, any additional electron removal has to come from the inner noble gas core. Since noble gas configurations are highly stable, it has to take a massive amount of energy to disturb that stability. And the same thing for these group 2 elements, right? That third ionization energy is going to be extremely large. So for beryllium, it'll have its first ionization energy will be a relatively fair number. That second one as well. But then once you get to that third ionization energy, it's going to be extremely larger, because at that point, after it's lost 2 valence electrons, it has noble gas-like configuration, which is highly stable. So in summary, ionization energy increases across a period and it decreases down a group. Removing an electron from a P4 configuration is actually easier than expected due to electron repulsion in comparison to removing an electron from a P3 configuration. So our example demonstrated to us that oxygen's ionization energy is actually lower than nitrogen's. Then we talked about successive ionization energies and how they increase dramatically, especially when you're trying to remove electrons from a noble gas configuration. We talked about alkali metals having a very high second ionization energy and alkaline earth metals having a very high third ionization energy. Let's go ahead now and tackle some problems. This first problem here says, which of the following elements has the highest first ionization energy? Potassium, sodium, chlorine, or neon? Let's go ahead and identify where these elements are on the periodic table, and then we can go ahead and answer the question with that information. Here is potassium right here. Here is sodium. Then we have chlorine over here, and then neon. Now, ionization energy, it increases across a period and it decreases down a group. This is due to increasing nuclear charge and electron shielding effects. Noble gases have the highest ionization energy in their respective periods because they have a stable full octet that strongly resists electron removal. So among the choices here, Neon is going to have that highest first ionization energy because it is a noble gas with a complete valence shell. So the correct answer here is D. The second question says, rank the following elements in order of increasing ionization energy. We have sodium, magnesium, silicon, and chlorine. Let's go ahead and identify where those are on the periodic table here. Sodium, magnesium, silicon, and chlorine. So we notice they're in the same period. What is our trend for ionization energy going from left to right? Well, going from left to right, ionization energy increases. Ionization energy increases across a period. And that means that the further right an element is in this period, the higher the ionization energy. So chlorine is going to have the highest ionization energy. Second highest ionization energy is going to be silicon, then magnesium, then sodium. So this is the trend we're looking for. All right. And that best aligns with answer choice A. Chlorine has the highest ionization energy, followed by silicon, then magnesium, then sodium. The third problem says, as you move across a period from left to right, ionization energy generally blinks. A says increases due to increasing nuclear charge. B says decreases due to increasing atomic size. C says stays the same across all elements in the period. And D says fluctuates unpredictably. Moving across a period, effective nuclear charge increases, and that's because protons are added to the nucleus without significant additional shielding. This increased attraction makes it harder to remove electrons, and it leads to a higher ionization energy. Therefore, ionization energy increases from left to right across a period due to the increasing nuclear charge. The correct answer here is going to be A. Finally, our last problem here says, a researcher collects ionization energy values for the elements sodium, potassium, and rubidium, but forgets which is which. The measured values are 4.34 electron volts, 5.14 electron volts, and 3.89 electron volts. Based on trends, which element corresponds to 3.89 electron volts? So we're trying to figure out from these three measured values, which element corresponds to that lowest ionization energy value. Ionization energy, it decreases down a group due to increased electron shielding and distance from the nucleus. Rubidium, potassium, and sodium, they're all alkali metals in group 1. So that means the element with the highest ionization energy would be sodium, followed by potassium, and then finally rubidium. Rubidium would have the lowest ionization energy based off of trends for ionization energy down a group. So the lowest value, 3.89 electron volts, this corresponds to rubidium, since it is the largest and most shielded element in this set. The correct answer is C. Finally, we can discuss electronegativity. Electronegativity is the ability of an atom to attract electrons in a chemical bond. Electronegativity, it increases across a period from left to right. This is because elements on the right side of the periodic table, particularly nonmetals, they have a higher effective nuclear charge, meaning they exert a stronger pull on electrons. Fluorine is actually the most electronegative element, while cesium is one of the least electronegative. Electronegativity also decreases going down a group. So as you move from top to bottom, electronegativity decreases. This happens because atomic size increases, meaning the valence electrons are farther from the nucleus and they experience more shielding. That reduces the nucleus's ability to attract bonding electrons. So if you're asked to rank elements by increasing electronegativity, always consider their position relative to fluorine. Values increase moving right and they decrease moving down. Now, electronegativity is not just a ranking tool. It helps us determine bond character by comparing the values of electronegativity between two bonded atoms. The difference in electronegativity between two atoms is denoted as delta En, which is simply found by subtracting the smaller electronegativity from the larger one. For example, let's determine the electronegativity difference for carbon and oxygen. We would simply take the difference, 3.5 minus 2.5, that gives us a difference of 1. So the difference in electronegativity for a carbon-oxygen bond is going to be 1. We can also compare different bond types by their electronegativity difference values, like you see in this flowchart. However, this is going to be something we cover later. I just wanted to provide you with an application of electronegativity difference values. So, in summary, electronegativity increases across a period and it decreases down a group. Then the difference in electronegativity, that's going to be calculated by subtracting electronegativity values for the bonded atoms. For the course you're taking with me, please make sure you remember these values. Let's go ahead and now jump into a couple of practice problems. This first problem says, which of the combinations of atoms has the largest difference in electronegativity values? Looking at our options, we have carbons bonded with 4 different elements: oxygen, nitrogen, fluorine, and hydrogen. And we have to determine which combination of atoms have the largest difference in electronegativity values. Now, you can approach this problem one of 2 ways. If you know that fluorine, if you recall that fluorine is the most electronegative element, then it becomes obvious that the largest difference between electronegativity values is going to be between carbon and fluorine. If you don't remember that fact, but you remember the electronegativity values, we can just go ahead and calculate that for each pair. For carbon and oxygen, oxygen has an electronegativity value of 3.5, carbon 2.5, so their difference is equal to 1. For nitrogen, the electronegativity is 3. For carbon, it's 2.5. The difference gives us 0.5. For carbon and fluorine, fluorine has an electronegativity value of 4, carbon 2.5. Their difference gives us 1.5. And finally, there's carbon and hydrogen. Carbon is 2.5, hydrogen is 2.1. Their difference gives us 0.4. Doing it this way helps us see that, in fact, the electronegativity difference value between carbon and fluorine is, in fact, greater. The second problem says, which of the following has the greatest electronegativity difference between its atoms? We notice that it's all hydrogens bonded with different halogens. And again, all we have to do here is recall that fluorine is the most electronegative element. So the difference between the electronegativity value for hydrogen and fluorine is going to be the greatest here. So the correct answer is D. And you can go ahead and calculate it to see for yourself. The third question says, if the most and least electronegative elements in the second period formed a bond, what would the electronegativity of that bond be round to the nearest 10? So let's go ahead and look at our periodic table. We are in period 2. The most electronegative element is going to be fluorine, and the least electronegative element is going to be lithium. Lithium and fluorine. Lithium has an electronegativity value of 1, and fluorine has an electronegativity value of 4. 4 minus 1 is equal to 3, so the correct answer here is D. Finally, our last problem says, why are the noble gases not assigned an electronegativity value? A says noble gases form bonds equally feasible with all other elements. B says noble gases are inert and hence mostly do not participate in bonding. C says noble gases are assigned electropositivity values instead. And D says they are all gases and gases do not have electronegativity values. Now, electronegativity, it refers to an atom's ability to attract shared electrons in a bond. But noble gases are generally unreactive because they already have a full valence shell. This means they rarely form bonds and thus do not have meaningful electronegativity values. That makes the correct answer here answer choice B. Noble gases are inert and hence mostly do not participate in bonding. With that, we've completed this lecture. Now, this last page you see here serves as a summary, a cheat sheet of the key periodic trends that we have discussed: atomic radius, effective nuclear charge, ionization energy, and electronegativity. The periodic table diagram highlights how these trends change across periods and down groups, and then the definitions for each of these topics are provided below. With that, I hope this lecture has helped. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.